Welcome to this BAA webinar, which is live, and it's also being recorded, and it's live on YouTube. You'll be able to ask questions using the Zoom chat, which is the preferred method, or you can also make comments on the YouTube stream, but those are more difficult to pick up, whereas we definitely see the Zoom Q&A. So when it comes to it, you can type any questions in the Q&A. So we have today one of the world's foremost experts on Jupiter, director of the BAA Jupiter section, John Rogers. And he is going to tell us about what is going on Jupiter. You may have noticed, if you've looked in the sky about 1 a.m. or 2 a.m. recently, Jupiter's become very prominent now. It's about 25 degrees high, and it's by far the brightest thing in the sky. So it is becoming well placed for observation now, although better placed from more southerly latitudes than the UK. And of course, the Juno spacecraft, which I think John is going to tell us some about some of the latest results, is still there. And there is extensive amateur collaboration pro-am collaboration between the Juno spacecraft team and amateurs worldwide studying Jupiter. So without further ado, I will hand you over to John to give you the latest developments.
Well, thank you, David, and good evening, everybody, or good day or good night, whatever time of the day or night it may be for you, wherever you are. As David said, I'm going to be talking both about what we can see in telescopically from the ground, and also what the camera on Juno is seeing from its orbit around Jupiter. And I'll be concentrating on what we can see this year and how that fits into the long-term patterns of features on the planet. I picked this title, Jupiter Rising, for two reasons. One, that, as David said, Jupiter is now coming up in the morning, and indeed it's only about 5 weeks until opposition on August the 20th. And also because it is now rising higher in the sky for those of us in the Northern Hemisphere. For several years, we've depended very largely on our friends in the Southern Hemisphere and the tropics, who continue to produce superb images, but it's been quite awkward for observers in the Northern Hemisphere. But Jupiter is now rising to a manageable altitude, and so this is just the time to brush down the telescopes and have a look at this giant planet. But I'll start off with Jupiter setting as we saw it back in December at the end of the last apparition. We were favoured with good weather in Britain for some of those nights, and so many of you will remember Jupiter and Saturn less than a degree apart going down in the evening sky. Here are some telescopic views that people from England were able to obtain, in fact England and Wales, I see. It was perhaps the only time in our lifetime when Jupiter and Saturn can be observed within the same field of view at reasonably high power in the telescope. Now, as Jupiter is coming further north, observers in Northern Europe are managing to get some images, and indeed a rather nice drawing here by Chris Nuttall in York. These are all images or a drawing from the last couple of months. The first three from England and the bottom three from France. So as you see, we can see interesting features on the planet, most notably this very orange-looking equatorial band occupying most of the equatorial region, the great red spot here, which we're all very familiar with. So I'll be describing some of these features during the talk. And I just want to show one more image, which is from England. Some may look on these works, you might see, and despair. This is taken by Damien Peach just a few days ago, but he assures me that it was not taken from Richard Branson's rocket, and it was not taken from Telescope, but it was taken from his home in Hampshire with the planet at an altitude of 27 degrees. So this is the amount of detail that is possible. Another aspect of Jupiter's orbital progression this year is that the system is currently edge-on to Earth and Sun. In fact, Jupiter's equinox was on May the 2nd. That's when we passed through the equatorial plane. And an important consequence of that is that the four big satellites pass in front of each other and cast their shadows on each other, so-called mutual phenomena, or as the French call them, phénomènes mutuels, so we call them FIMUs. Here's a drawing also by Chris Nuttall showing a rather nice occasion when Ganymede eclipsed Io. So here is Io. Here is Ganymede in front of the planet, and it casts its shadow on Io, and Io passes through it in a few minutes. Some observers in Australia and South Africa have been able to take videos of some of these events. This is Ganymede as the shadow of Europa passes over one pole of it, as taken by Phil Miles in Australia. And the same event was also imaged by Anthony Wesley, a neighbour of Phil Miles. Here is Ganymede with the shadow of Europa passing over it. And at the same time, here is Callisto emerging from occultation behind the planet. Anthony took another video, this time showing the shadow of Callisto sweeping across Ganymede. This should say being eclipsed by Callisto. And this is a central passage of the umbra, which looks quite small because Callisto has quite a large penumbra because it's so far from the other satellites. There was also a lovely event imaged by Clyde Foster in South Africa, which I can't show you the video of because it wouldn't embed in the PowerPoint, but I can show it to you afterwards if we have time. On this occasion, also Ganymede was eclipsing Io. So here's Ganymede, here's Io, and both of them were casting their shadows on the planet at the same time. So as the eclipse happened, the two shadows merged and then separated again. So this is another picture of Clyde a bit later in the night when the seeing was a bit better. And I show it because it's a nice illustration of the fact that while these satellites are passing across the equatorial region, that means that the planet is close to equinox. And you can see this main feature of the equatorial region at the moment, which is this ochre or orange equatorial band. Now, of course, Juno is in orbit around Jupiter, and every 53 days it takes a suite of superb high-resolution images from pole to pole. So we thought there's one more possible consequence of Jupiter passing through equinox that might be seen at high resolution, and that is that perhaps we might see the shadow of the ring projected onto the equator. Well, Juno only takes images when it comes to perijove, so we couldn't take them on May the 2nd, but Juno Cam was taking images 2.5 weeks earlier. Let me explain the reason why this happens, in case people are not familiar with Juno. Excuse me. It's in a very elliptical orbit with a period of 53 days. So all the science and at least all the pointing science concerning Jupiter itself is done during a matter of hours surrounding the perijove. That is the time of closest approach to Jupiter. So this is a rough sketch of the orbit at its perijove 33 flyby on April 16th. It applies to all of the recent perijoves. Juno comes in fairly low over the North Pole. It sweeps to its closest approach, 3,500 kilometers. It is currently over the North Temperate Zone. And then it sweeps also pretty low over the equatorial region, but it's climbing, and then it climbs up high as it passes out over the Southern Hemisphere, close to the South Pole. So we looked at these images taken on April 15th to see whether we could see any shadow of the ring, and I'm afraid that the answer is no, we couldn't, which is exactly what one professional planetary scientist we consulted thought would be the case, but it's always worth looking, isn't it? One can't always rely on predictions. This is Juno Cam's image looking due east along the equator, which runs more or less here. If you can see faint vertical banding here, those are artifacts of the camera system, so let's ignore those. But what you can see is fascinating details of the clouds over the equatorial region, which we see at every perijove currently. So here is the orange band, and the panel below is a full resolution version of that part of this image. You can see some of the flanking cloud bands. Some look orange because of probably because of this overlying high altitude haze. Some look white, then there are dark streaks, which may be thinner regions of the clouds. You can see a lot of wave phenomena. They're called mesoscale waves, and they're quite prominent, say here, for instance, running roughly horizontally in this image, roughly transverse to the east-west direction. There is another series affecting this white cloud band. But you can also see them very faintly, very low contrast over much of this image. I mean, all this region, there are very faint horizontal striations, which are also these mesoscale waves. Wavelength, I don't know exactly, something of the order of 100 kilometers probably. And you see them out here on the other side as well. So some of the space scientists involved in Juno are currently interested in following those mesoscale waves. So let's turn now to the features of the planet itself. And now we're onto the equatorial region. Let's look at this coloration event. This is an example of one that's a familiar event in Jupiter's history, and they occur at intervals of several years, somewhat irregularly. But the one we're seeing now has been going on since 2018, and it's the most intense and the most prolonged since 1989 to 91. Here is another beautiful color image of it. And I also want to introduce the methane band imaging, because that is showing us a lot about the equatorial band and about other features on the planet as well. Images in the methane band are taken at the near infrared wavelength, 0.89 microns, because that's a methane absorption band. And methane is a gas that's uniformly distributed in Jupiter's atmosphere. And as it absorbs at this wavelength, an image taken at that wavelength basically shows the altitudes of the clouds. Because if the infrared light penetrates deeply down into the atmosphere, as it does in the belts, for instance, then it mostly gets absorbed by the methane. But if it encounters high altitude aerosols, the high altitude tops of clouds, as it does over the equatorial region currently, then it gets reflected. And so high altitude things look bright in this waveband. So it's a very useful tool for getting information about what is going on with the meteorology of the planet. You can see here the great red spot, although it's on the limb in this image, is also very bright because those red clouds go high up. But also these polar hoods over the South Pole and the North Pole are methane bright high altitude features. I should have mentioned, by the way, all the images in this talk have north up unless otherwise stated. So this coloration event started to develop in spring 2018. This is a series of panels of maps from 2018 up to the present, just showing the belts of the planet from 50 degrees north to 50 degrees south, showing the large-scale changes in them over this period. As for the equatorial coloration, 2018, the planet was actually pretty normal. In 2018 March, the equatorial zone is normally white or off-white with some grayish or bluish streaks in it. But coloration had come on by 2018 May, and it intensified during 2018. In the first half of 2019, it was very intense as it ever gets. Then it seemed to be fading again in autumn 2019, quite clearly so as 2020 began. However, it was then renewed in the second half of 2020, and so now it's again as intense as it's ever been. It's always been predominantly in the equatorial band, that is spanning a few degrees either side of the equator, though at its most intense it's also spread variably or more weakly over the northern equatorial zone here. The only bit that has remained purely white is this very narrow strip of the southern equatorial zone. You can also see changes in the north equatorial belt here, which I'll come on to later in the talk. One fascinating aspect of this has been the discovery of a series of waves that are along the southern edge of this methane bright band, which are not moving at all as one would expect the features of the equatorial zone to go. Jupiter has several longitude systems defined in order to track characteristic features of the planet. And the interior of the planet, the reference point for all the atmospheric features, is called System 3, and that is also pretty close to the rotation period of many features in the high latitudes. For instance, these white ovals that have been marked in purple here. On the other hand, the equatorial region, including these dark features along the edge of it here, all moves very rapidly to the east and is tracked in longitude System 1. When I say very rapidly, I mean 7 to 8 degrees per day, typically, and even faster if you look at certain features. So this is all the great equatorial current or jet stream. And nothing has ever been seen in the equatorial region that moves with System 3, either is stationary with respect to the other features on the planet. Until last year, when we noticed this pattern of waves along the edge of the methane bright band, which is still definitely within the equatorial zone. I mean, that band corresponds to the orange band, and although these waves are not visible in visible light, that's really because that edge is obscured by streaks of various different colors, and so one can't make out the edge of the haze band itself. But when plotting the positions of these waves over several days and weeks, it became clear that they were not moving with System 1 at all, not moving to the east. They were stationary in System 3. Here are measurements of their longitudes up here in System 3 versus the time spanning 45 days across here. And so one is stationary at this longitude, one is stationary at this longitude. So, and 4 of them were pretty much stationary during that period. And indeed, similar stationary waves were visible again in July and August. They may well have been the same waves that just hadn't tracked in between. And this year, there have been some similar features visible, but also an even more remarkable development. Shown here in this series of animated maps made from observers' methane images by Shinji Mizumoto. So this is a series of maps plotted in System 3. We focus on this bright patch here, which spans the entire equatorial region. You can see on its north side, it's anchored in a few of these waves, similar to last year's waves, although the array of them is not so well defined. But it's also a bright patch that spans the whole equatorial region and gives rise to a streak here that does move a bit to the east during this series, although not nearly as fast as the other features of the equatorial region. These were taken in May and June this year. So this is something that has interested professional planetary scientists a lot. And the leading hypothesis for what we're seeing here is that it could be due to the very high altitude of the aerosols in this equatorial band. It's expected that if you go high enough in the atmosphere, the jet stream will decay to nothing, but features will be more or less stationary with respect to the rest of the planet. And it may be that for the first time we've detected features of a very high altitude haze in the equatorial band that are high enough that they are reaching that level in the atmosphere. So that's the subject for further research. Okay, we now want to move on to the rest of the planet. And I start with showing this beautiful movie that is actually 21 years old. It was from the Cassini flyby in 2000. But it's a classic movie for showing the movements of winds on the planet. It's taken over, I think, several weeks in December 2000. And you can see, obviously, how the whole equatorial region moves very rapidly to the east, to the right. Then if you look up into other latitudes, you can see another very rapid jet stream here and another rapid jet stream here, all moving east, but you can also see some moving to the west. So there's one along here moving to the west, others in other latitudes. And basically these jet streams form an alternating pattern as you go up in latitude, which define domains on the planet, and each domain corresponds to one of the classical belts plus zones. So now let's take a look at the 4 major domains and see what's been happening in them recently. let me just summarize here what they are. So the North Temperate domain covers the North Temperate belt and zone and is here. That underwent a huge great upheaval, a cyclic upheaval that happened every 4 to 5 years in 2020. And it calmed down a lot since then and is now really quiet and normal. The North Tropical Zone comprises the North Tropical domain comprises the North Tropical Zone and the North Equatorial Belt, NEB. That also underwent a cyclic upheaval in 2020 and has now calmed down. However, it's become so quiescent and faint that it's become very interesting again. The South Tropical Domain is pretty normal at the moment. There's still some disturbance going on here in the South Equatorial Belt, just adjacent to the Great Red Spot. But the main focus of interest in that at the moment is in the Great Red Spot itself and this disturbance that you can see around it. And then finally, we'll look at the South Temperate Domain, that is the South Temperate Belt and Zone, STB, where we're looking at a sequence of so-called structured sectors that appear and disappear within the zone over a matter of years. Okay, starting off with the North Temperate Domain, maybe just quickly summarize what happened last year. There was this upheaval beginning with the outbreak on the North Temperate Belt South Edge jet stream, which is quite a mouthful, but it's the most rapid jet stream on the planet and one of the most spectacular phenomena to occur on the planet. And it consisted of these 3 brilliant plumes that erupted suddenly, the first one on August the 18th last year. And as always happens in these outbreaks, they appeared at different longitudes. They moved very rapidly around the planet with the jet stream in that latitude. Following each one, a series of waves and dark spots appeared, and all this disturbance spread around the planet within a month or two. And then we ended up with a scene of intense turbulence, and the NTB revived as a result. The North Equatorial Belt upheaval had occurred a few months before. It was a so-called NEB expansion event, because these events consist of the north edge of the belt, the belt expanding as the north edge of the belt shifts up a couple of degrees in latitude. So here's another sequence of those map panels showing, starting here in 2019 when the belt was pretty normal. Then in spring 2020, a great deal of disturbance erupted within the belt, so-called rifts, which are convective disturbances that gradually go bigger and spread around the belt. And within a few months, it was evident that this rift activity was leading to expansion of the belt towards the north. So by July, the belt was expanded northwards to its maximum latitude around almost the whole planet. And so this was a classic NEB expansion event, and occurred. They've been occurring every 3 years lately, and this one occurred 3 years after the last one. But just then, this NTB outbreak occurred and led to even more disturbance in the region. And so by October, November, the whole region from the North Temperate Belt up to the equatorial, the edge of the equatorial zone, had become intensely turbulent and also reddish. That was actually a very interesting phenomenon, not just in itself, because it was spectacular, but also in terms of the question of whether there is any connection between these two disturbances in adjacent domains. Because this is now the 3rd time we've seen such a conjunction of the NTB and NEB disturbances happening within a few months of each other and leading to this appearance. The 3rd time in the last 10 years. First time was in 2012. You see a picture from 2012 here. There was another such occasion in 2016-17. It's very hard to tell whether this is a real relationship or just coincidence, because the upheavals in these two domains have been happening with similar periodicity of 3 to 5 years. And the origins of the outbreaks that initiate them have not had a fixed relationship in time. Sometimes the NTB has appeared first, sometimes the NEB outbreak has appeared first. So I think unless some theoretical reason appears why there should be a connection between these two, we just have to wait another decade or two to see whether they continue to happen at the same time. But it's a fascinating thing to keep on observing over the coming years. What about Juno? Well, every 53 days, Juno CAM has taken a beautiful series of images over the whole of its track. So it's recorded the cloud textures of whatever happens to lay beneath it in the NTB and the NEB during these upheavals. We haven't really assembled all these images together into high resolution maps yet. It's something for future researchers. But these are just a few snapshot samples, a few sort of thumbnail samples to show a wealth of data exists to show these images covering the NTB and then the NEB. Here they've been put together into a low resolution map. This was at the height of the Great Northern Upheavals, we could call it, in November. Here it is 3 perijoves later this April, when everything has quietened down tremendously. At high resolution, though, you can still see turbulence in these belts. Mind you, you see turbulence on this level everywhere on Jupiter, but it's on a very small scale. And it's an illustration of how turbulence in these events gradually progresses from large scale that dazzles us all to small scale that from Earth looks absolutely quiescent. And likewise in the zones, they're now both white and quiescent. And you see lots of these little tiny white spots, which are so-called pop-up clouds. When they're seen closer to the terminator, they cast shadows. They're clouds just a few kilometers or tens of kilometers across. This is a good point at the talk in which to point out that there's a great synergy between the Juno observations and amateur images. And not just Juno CAM, which was initially put there in order to engage amateurs in the image or in the mission, although it's also producing excellent science. There's one of Juno's prime instruments, the microwave radiometer, which probes the atmosphere down below the clouds. And that also focuses on a narrow swathe along Juno's track, which will be kind of down here during a given perijove. And it's important from the point of view of those scientists as well to know exactly what it is looking at a particular perijove. So we need the amateur images to put this narrow field of view of Juno CAM and the narrow field of view of the microwave radiometer into context, so we can say what type of features are actually being shown. And also to put it into temporal context, so we can say how these phenomena have been developing in the 53 days between perijoves. So I hope people who are taking good images are uploading them all to the usual databases, and including the Juno CAM database itself, which is accessible on the Juno CAM website. And please do carry on taking images and uploading them, and also sending them to us in the Jupiter section over the coming years of the Juno mission. So this is an example of a ground-based map. As you can see, ground-based imagers can obviously see the whole planet over a matter of 2 or 3 days and produce a map that is now of pretty good quality. So what's happening to the NEB now? Well, it is receding and fading. The NEB south component is still dark, as you can see along here, but the rest of the belt is fading rapidly. Apart from these dark cyclonic circulations, which are now extremely dark and prominent. They're called barges because old-time visual observers looked at them and said, it looks a bit like a barge. So that name has stuck. Now, this is a state of the planet that's only been observed a couple of times in the last century. In fact, only once during most of our living memory, which was in 2012. And it leads on to a phenomenon called the NEB revival, which is like an NEB expansion event, as we saw last year, but probably more impressive because it starts from a totally quiescent belt. Now, this happened in 2012, but unfortunately, it happened during solar conjunction. So we really hope that we'll see the next one during an opposition period. But a century or more ago, these NEB fades and revivals happen quite often. So in the 1890s, we can see one here. Now, all old data has south up. So here, south up, and this is the NEB in its shrunken state in February 1896. But in December that year, Something happened here on the NEB, and incidentally, the equatorial zone had then become coloured as well, as it is now. And the disturbance spread around the north part of the NEB over the subsequent several months. And the outcome was revival of a very broad NEB. Now, in those days, with visual observations, the details of this phenomenon couldn't be tracked. We know that they were sometimes, as in this instance, pretty spectacular events. And so let's hope that we see one in the near future. This is what happened in 2011, 2012. Here again, south is up, and in this, here was the belt fading and the barges becoming prominent, just as is happening now. And here it was 6 months later in August, when the revival had pretty much happened, along with the revival of the NTB, incidentally. So this is the Great Northern Upheaval appearance. Well, given the 3-year periodicity of these events, and the fact the last such upheaval was in 2020, I would expect that we'll have an NEB revival in 2023. So let's hope so, and let's hope that it happens while the planet is actually observable. So here's the status of the planet now, moving back to north up, with Damien's beautiful image showing those intense barges. Okay, let's move on to the South Tropical domain, the Great Red Spot. Now, excuse me. You probably all know, it's got a lot of publicity recently, that the Great Red Spot is shrinking and has been shrinking for at least the last century. So here's a sequence of images documenting that, with north up this time. And now in 2021, it's smaller than it has ever been before. So why is that? Well, in part, it just seems to be long-term shrinkage, and in part, it seems to have been triggered by some events that became particularly prominent in 2019, the production of what we call red flakes. These are best seen in these Juno images. What happens, we discovered in 2019, is that these rings on the SEB south edge, which are coming in on a westward jet stream, and are anticyclonic vortices, they come along, they get swept around the Great Red Spot, and this is well known. But what they were doing in 2019 was tearing out these red flakes from the spot. There happened to be one in place in each of these 3 perigems. And this one was a bit older than the others and had spread out very flamboyantly. They're also prominent in the methane band images. You can see them here in amateur images, but they're better shown, of course, in a Juno image, because the Great Red Spot, consisting of high altitude cloud material, evidently it's that high altitude cloud material that is being pulled out to form these flakes, and they're also methane bright. So what's been happening since then? Oh, excuse me. Well, some flakes have still been happening this year. A lot of those SEBS rings or vortices have been coming in and have been producing some flakes. This is a pair of images taken just one rotation apart, 10 hours apart, and you can see how this flake has appeared in one image, and in the next image, I think it's moved around here and got squeezed, and another one seems to be being induced at this point. This is the sense of rotation of the Great Red Spot. But the more conspicuous feature that we're seeing at the moment is this great big so-called hook, with a lot of the turbulence that is always present just following the Great Red Spot extending into the hook, and it extends in a so-called collar. Sorry for the mixed metaphors in these names that we're giving, and that then extends in the preceding the easterly direction to form the South Tropical Band. This has been particularly prominent this year. I mean, these are not uncommon appearances, but it's been particularly prominent this year. In fact, it began during solar conjunction, and it was first discovered in Juno images in February. In these fairly low resolution images from Juno during its outbound pass in February. And this hook and collar and band appearance has remained ever since. These 3 lower images are taken intervals just 3 to 4 days this month. And you can see another of those SEB South rings coming in here, indicated by the red arrow, and moves around here. I don't see it necessarily inducing a flake, but you can see how the collar here and the hook are continuously disturbed by all these features. Now, during this period, the great red spot has shrunk again. During the peak of the flakes in late spring 2019, the great red spot shrank from about 14.5 degrees, which it had been at for several years, to its smallest size ever, just over 12 degrees long. But then when the biggest flaking events ceased for a while, the great red spot recovered its size. Then last year it began shrinking again, for no obvious reason, because there were not very prominent flaking events last year. It shrank to about 12.5 degrees long, and it's still at that size now. There's sometimes when these impacts occur on it, it dips down to even smaller lengths, only 12 degrees long. So again, this is something to be monitored over the coming months and years, because the great red spot is still shrinking, and it causes us to start thinking again, could it actually disappear within our lifetimes? Or more likely, could it undergo some kind of transformation which will renew it, so that there is still some large anticyclone in the south tropical domain? Something to keep an eye open for. Let's have a look back at the Cassini map, and I'll show you that now, partly to show the rotation of the great red spot. It was almost twice as big back in the days of Cassini, or 50% bigger anyway. And there were lots of these SEBS rings coming in then, and they were interacting with the great red spot. But they weren't disrupting it in the same way that it has been disrupted in the last 2 years. Another thing to show you now is up in the south temperate domain, which we'll come on to, this dark feature here. Because the south temperate belt has been largely whitened and placid over the last 22 years. Except for a limited number of so-called structured sectors. And this is one of them. This is a particularly dark and turbulent one. And you can see that turbulence and the rotation in it. It's a cyclonic feature circulating in this direction, opposite to the great red spot circulation. And you can see it ejecting more spots on this jet stream going to the east and on this jet stream going to the west. And this year, we seem to be following the origin of another of these features. So that's been the main feature of interest in this domain over the last few months. Now, this has been an ongoing story for some 22 years, as structured segments within this domain have repeatedly appeared and drifted eastwards relative to oval BA very slowly, and have then collided with the dark segment following oval BA, and a systematic sequence of changes has taken place. This series actually starts in 1998, but here is a Cassini map of which you just saw a portion around here. So the dark segment I just pointed out was here in the Cassini imagery. It's labeled segment B, and it gradually expanded and it moved towards oval BA, which is the one big anticyclonic oval in the domain. And when it reaches the dark feature following oval BA, which is here in the map, I think you can hardly see it, but take my word for it, it becomes merged into a long dark turbulent segment, and oval BA is accelerated towards the east in its long-term drift. And this then lasts for several months or years until it eventually dwindles to a small spot and BA decelerates again. And a series of these structured segments have appeared, always some tens of degrees preceding BA, in the form of either a very dark spot or a dark grey streak. And so you can see in this chart that a number of them have appeared. Some have been pale, low contrast features, but still powerful cyclonic circulations. Some have been dark, turbulent features. So for a couple of years, I've been expecting a new one to appear in this region, and it's been a bit overdue, but it now seems to have appeared, and we saw a couple of candidates appearing in 2020. So this is images from mid-April, maps from mid-April, a ground-based one and a Juno cam one. Here's oval BA, the anticyclone, which at that point was white. Well, here's one very dark spot that had recently appeared, which we went on to call went on to call dark spot 6. And here is a very low contrast feature, but it seemed to be a persistent little streak with possibly a spot in it which we thought might be a cyclonic vortex, and so it needed to be monitored. Well, JunoCam got some very good images of these features and similar ones around that time. Here's that dark spot 6. You can see this beautiful cyclonic spiral around it, and it may be a very deep hole in the center with some rather irregular reddish clouds floating over it. Here is a very low contrast cyclonic feature, probably similar to that pale streak I just showed you. Clearly, as imaged in JunoCam, this is a little cyclone. And it was in a little cyclone that a new feature suddenly appeared last May and attracted quite a lot of publicity. It was discovered by Clyde Foster and became known as Clyde's spot, because what it was a very methane bright spot, small, transitory, but it's growing into something that I think is going to be much bigger. It was particularly well observed by JunoCam, which already was scheduled to observe that region 2 days later. And while the methane bright spot rapidly faded, and indeed at visible wavelengths, it gradually turned into a dark spot. JunoCam got these beautiful images just 2 days after the initial outbreak and showed that indeed there was this cyclone at that point, and the bright outbreak was a high-level patch of cloud that appeared to be spreading over the central regions of that cyclone. It was one of these convective plumes that grows up from below vigorously, convecting into the upper atmosphere, and can then initiate a disturbance. In this case, it was a very localized disturbance because it's remained within this cyclonic circulation. And in ground-based images, it's been difficult to tell exactly what it is because it's remained as a rather small and irregular darkish spot, which we call dark spot 7. However, in the last couple of months, JunoCam has twice got really nice images of it, as it happened to fly near that longitude again. And what it's shown is that this little irregular dark spot is in fact a classic chaotic cyclonic turbulent region. We call it FFR, which means folded filamentary region. That's the Voyager scientist name for this kind of feature. And it's growing. Here it was imaged at perigeo 33 in April, here at perigeo 34 in June. And it clearly is growing. And so I think now there is little doubt. Here's the close-ups of them. I think now there is little doubt that this is going to carry on growing into a classic cyclonic dark segment of STB. Meanwhile, incidentally, dark spot 6 has moved closer to oval BA and has turned into an orange spot as seen by JunoCam, although fading, here it is again, but it's a bright white spot as seen from the ground, because ground-based observers use slightly different filters from JunoCam. And so I guess we need to change its name to white spot 6 now. So we will follow that over the coming months and years. Here are the latest images of it in June and July. So this is Clyde's spot here. This is oval BA. This is white spot 6, and this is Clyde's spot, which, as you can see, appears to be emitting a great deal of disturbance preceding and following it. So it's an interesting question whether this will continue to expand and will be the next STB structured segment, or whether all this disturbance means that it's going to fill up this entire sector here with dark material and produce a revival of the STB on a grander scale. Watch this space. Now, in the last couple of minutes, I should briefly tell you about NASA's Juno orbiter and its extended mission, because the mission should have ended this month, according to the plan that has been followed over the last 4 years. But fortunately, NASA have granted a 4-year extension to the mission because it's producing such good science. And so it will carry on for another 4 years. And in that time, it will be having some satellite flybys of Ganymede and then Europa and then Io, which have the beneficial effect of reducing the orbital period from 53 days to 43 days and so on. And in fact, the first of these happened at the last perigeo on June 7th, perigeo 34. It was a flyby of Ganymede, and it gave rise to superb imagery by JunoCam. We weren't sure if JunoCam, as it had been designed for very special lighting and very rapid flyover conditions close to Jupiter, would actually be able to take good images of the satellites, but it passed the test with flying colors, passing just 1,000 kilometers above Ganymede. Here is a larger resolution clip from one of those images. And in fact, just before this meeting started, I noticed in my inbox an email from the JPL newsletter system showing that a superb video animation of this flyby, along with the flyby of Jupiter 14 hours later, has just been posted on the JPL website. So go to that site to see more of this flyby. So this diagram, which comes from a talk by Scott Bolton, the mission leader, shows how the orbit has been evolving and why it's now possible to have these satellite flybys. When the mission started, the orbit was, as we said, highly elliptical and more or less perpendicular to Jupiter's orbital plane, passing over the perijove over the equatorial region. But due to natural orbital perturbations, the perijove has gradually been drifting to the north, and that means the whole orbit is gradually tilted. And so now the inbound leg comes in more or less at the orbit of Ganymede. It crosses the equator at the orbit of Ganymede and then moves over and moves out to high over the South Pole. So that meant that a Ganymede flyby was possible, which has been used to tweak the orbit to reduce the orbital period slightly. But it's still an elliptical orbit. The perijove is still progressing northwards. And so a bit later, there will be a flyby of Europa, which will be used to reduce the orbital period a bit further. And later, a couple of flybys of Io. And I really look forward to seeing the images that JunoCam will get from that flyby. That is assuming, of course, that all the systems on the spacecraft continue to work fine. They are currently working fine. Any radiation damage is really minimal. Radiation damage will be worse during the extended mission because these inbound legs are now going to be taking place through Jupiter's radiation belts, especially as it gets close to Europa and Io. And so we don't know quite how the instruments will respond to that level of radiation damage, but we still expect them to carry on working to some extent, at least, hopefully just as well as they are now. So there are science objectives which include continuing the main mission, as it has been so successful up to now, but also studying the satellites, getting more extended and high-resolution views of a magnetic feature that Juno has discovered near the equator in Jupiter, and of the core of Jupiter, which has turned out to be not as expected. And also continuing to study the atmosphere, both from the radiometer and from JunoCam, looking particularly at the northern hemisphere. Now we're passing close over that, which should lead to plumbing the depths of the circumpolar cyclones that have kept us all so interested. Okay, and this is just a series of views of the orbits as seen from over the North Pole, demonstrating how they shortened during the extended mission. But I won't dwell over that, just to say that JunoCam should still be getting images as long as it lasts, which may well be the full 4 years. And so our and your amateur images will still be essential for providing context for those images. And really, we and the JunoCam team will continue to look forward to seeing them. So thank you very much for your attention, and I'll be very happy to answer any questions that we can.
Thank you very much, John. That was extremely fascinating and some extremely up-to-date information. I hadn't seen those pictures of Ganymede, which are absolutely remarkable. And a lot to look forward there, with the mission being extended for 4 years. That is a great boost. We've got a question here about Ganymede, actually. Daryl Dobbs has asked, on the picture of Ganymede taken by Juno, there was marked fresh impact crater. What does this mean? How fresh is fresh? Is that post?
Oh, it means possibly 1 billion years old. So sorry, it didn't happen yesterday. The point is that these impact craters, which are obviously ray craters similar to those on the moon, have got very extensive ray systems around them. So you can see that they're pretty old. Sorry, they're pretty new in geological terms, compared to this, which is a very old impact crater. Because these impacts are into an ice crust, the impacts weren't exactly the same as they were on the moon. And the older ones, which you see here into the oldest terrain, well, this one into the oldest terrain, the impact went into a rather soft iced crust, may even have penetrated partly through into the water ocean below at the time. And so the craters collapsed at the time they were forming or very soon after. So as the crust got thicker over the years, the craters became more substantial. So these obviously are pretty good, impressive craters. But the more recent ones look much more like lunar craters and have these rays prominently around them.
So I cannot see any other questions at the moment. This surface that we're looking at in Ganymede, this is icy, isn't it?
Sorry, I'll start sharing again.
This,
if I can see the, oh, where's share screen? Oh, there we are. Yeah, sorry.
the groovy surface is ice, isn't it?
Sorry, we've all gone back to, here it is. Oh, here it is. It's reappeared. Yes, the crust is ice, but sort of dirty ice. The old terrain, where you see a lot of old craters and furrows, is very dirty ice. But this grooved terrain is brighter and is less dirty ice. And in fact, that's why the impact craters that happen on that terrain produce these very bright rays. Even old ones produce a visible ray pattern. In fact, you can see that very clearly in the case of this crater chain, which came in from a shattered comet, rather like Shoemaker-Levy 9. It was noticed at the time of those famous comet crash impacts on Jupiter that similar shattered comets must have produced these crater chains on Ganymede. So this was obviously all formed at a single moment, and you can see it produced bright ray material where it happened, where it hit the grooved terrain, and not where it hit the old dark terrain. So that indicates that the ray material is produced by impacting onto reasonably fresh ice.
But it's all pretty old, really. We've got, I think Darrell was hoping for some evidence of change since earlier spacecraft like Voyager.
Well, I think one of the mission objectives is to look at these JunoCam images and see whether they can see any new craters. But I think that would be quite a long shot. Incidentally, these JunoCam images, while some of these features, including this crater chain and some of these very characteristic features, were imaged at slightly higher resolution by Galileo, parts of this terrain have never been imaged previously at such high resolution as in this JunoCam image, because Voyager covered parts of the planet well, but others not so well, and Galileo was limited in its high resolution imaging to imaging certain regions.
Mike Fuchs has made a comment complimenting you on a great talk. Given the great red spot has been shrinking and showing the shredding features, do you think it will disappear? Well, that's the $1,000,000 question, is it? Will it disappear? And
I think it is more likely that it will be renewed in some way. We've seen this with the ovals in the south temperate region. There were 3 of them up until the 1990s, and they were shrinking, and then eventually they merged into one oval, oval BA. So now we have one big one. But you also see smaller anticyclonic ovals appearing in that domain. Looking at the pattern of anticyclones over the whole planet, I think it's necessary to have some in every domain. And in these low latitude domains, it seems necessary to have either a number of medium-sized ones, as in the North Tropical zone, or one huge one, as in the South Tropical zone. That is the Great Red Spot. So it is still shrinking and could lead to disappearance in our lifetimes. I mean, the rate it is shrinking, it could become totally circular, which doesn't look like a very stable condition for such a huge object within our lifetimes. However, features like south tropical disturbances can appear. That's a reconnection of the jet streams that can cause a large-scale circulation that could, in principle, evolve into the Great Red Spot, something like it. So I think it'll be more complicated than a simple disappearance. It may be swallowed up in some larger feature that develops. Certainly, it'll be something to keep an eye open for if we get new south tropical disturbances appearing. Incidentally, I mean, we're also watching for something similar to happen in the south temperate domain, because there's now only the one big anticyclonic oval. And some of these structured segments I've been pointing out entail a certain amount of anticyclonic circulation just south of them. So we need to keep our eye on those as well, actually, and see if any of those could evolve into larger anticyclonic features, as well as the cyclonic belt segments.
Yes, so that's the thing about Jupiter. It's very dynamic, and one good thing about the Great Red Spot getting smaller, incidentally, is that it's very easy to see in small telescopes because it is such an intense contrast with the rest of the planet. And I've shown the Great Red Spot to people who've never looked through a telescope before, and just with a 4-inch telescope, 100mm telescope, and they've been able to see the Great Red Spot. And I'm sure that wasn't the case, wouldn't have been the case 10 years ago and more. It's because it's become so intensely coloured in the last few years.
Yeah, that's absolutely right. In earlier years, it would become very obvious, intensely coloured, just when the South Equatorial belt faded and was whitened. So the area around the Great Red Spot became whitened. But for most of the time, it was embedded in the South Equatorial belt and wasn't so obvious as a coloured feature. And it was usually quite faint in terms of colour. As you say, this year it has really become in the last several years, it's become very intense in colour, and a joy to look at.
Indeed. So here's a question from David Swan. On Jupiter's rings, the rings around the planet itself, you commented that the shadow has not been observed. What was that expected? The lack of a positive observation is telling us something about the density of the rings, or is it an issue with the imaging system?
No, it actually was expected, because we raised this issue with a professional space scientist shortly before, and he calculated that from what was known of the ring, it would be very unlikely to cast a shadow. It just didn't appear to be dense enough. But hey, Juno Cam was going to take the images anyway, and obviously they've targeted one for directly over the equator, and so it was certainly worth looking at the images. So it was always possible that calculations based on the previous longer range observations of the ring might have been inaccurate, but it turns out no, it is a very flimsy little thing, that main ring. Incidentally, as you see from this diagram, Juno's last orbits would actually pass through some of the outermost parts of the ring, not the main ring, but so-called gossamer rings and an inner halo. I mean, it already picks up a few dust particles as it passes through the equatorial plane, and presumably it will pick up rather more of those as it enters the gossamer rings. But they're called gossamer rings because they are exceedingly thin and just seen in images from Galileo, where it was looking against the sun, so any slight haze would catch the sunlight. So it's no danger to the spacecraft either. We don't expect there to be any large particles anywhere near that ring.
Jupiter is a dangerous place, of course, a lot of radiation. So
yes,
it's good that the spacecraft has survived so well so far.
Yes, and of course, given the fact that it is moving closer to the planet, exploration of the Io Europa Taurus, that is a torus of radiation belt in and around the orbit of Io, has been made one of the new science objectives. We hope it doesn't kill the spacecraft in doing so, but I hope we're for some really nice images of Io's volcanoes. Incidentally, I haven't put any images in, but one of the other instruments on Juno can already see Io's volcanoes. It's the Jovian infrared auroral mapper. Its main purpose is to look at the aurorae, but basically it's a high resolution thermal infrared instrument, and it can take images, and it's produced a lot of images showing Io as a dark disk spotted with dozens and dozens of little hotspots, which are the volcanoes. It has higher resolution than JunoCam, and so GeoRAM is already detecting changes in Io's volcanoes over the months and years.
I'm sure that will be a thing that amateurs will be trying to achieve in the future, to see if they can image any changes on Io and any evidence of volcanic activity.
Yeah, we need to be able to move into the thermal infrared beyond 5 microns or beyond.
Right.
It's a big challenge.
So here's a sophisticated question from Olaf. Can some of the atmospheric patterns on Jupiter be simulated numerically or using rotating spherical liquid models?
They can. There has been a big history of simulating the atmosphere of Jupiter, and he mentioned rotating liquid models. So Olaf, you're probably aware of some of that science that's been done. Models like that can reproduce cyclones and anticyclones and show that they can merge together in some respect similar to the atmosphere of Jupiter. And also, as you say, Olaf, there are computational models. In particular, there's one called EPIC that our colleagues at the University of the Basque Country in Bilbao have been using a lot. And in fact, several papers have been published in the last year where Agustin Sanchez de Vega and his colleagues there have collaborated with the JunoCam scientists and also with amateur observers who've been studying some of these phenomena, like the flaking of the Great Red Spot and the NGB jet stream outbreak. And Agustin's team have done simulations using their EPIC program, trying to reproduce the phenomena that have been observed in those cases, and have reproduced them fairly successfully. And this gives them a handle on how deep these phenomena would be, because that's one of the adjustable parameters in the EPIC model. And so, for instance, it enabled them to say that these flaking episodes are probably quite superficial, because the various aspects of the model and the simulations indicated they could be well reproduced by bringing in fairly superficial vortices, which are the SEB south rings, and that will tear off the high altitude layers, the red methane bright layers of Jupiter's Great Red Spot, but they don't necessarily disturb the deep circulation of the Great Red Spot much.
Well, that's amazing that actually progress has been made on that. It's difficult enough to predict the weather of the Earth. So having a completely different system, but in some ways similar on Jupiter, would be an interesting challenge, and that obviously atmospheric scientists would be keen to have a go at that, I think. And see
it is, and I haven't said anything about Juno's other experiments really, but one of the aims of the mission is to sense how deep the Great Red Spot goes, and I believe that the infrared radiometer can sense disturbances of the spot down to maybe 300 kilometers or so. On the other hand, so far the gravity flybys have not seen any disturbance by the Great Red Spot, as far as I know. Both of these are work in progress and depend a lot on modeling, so I don't know exactly what the last word is on either of those experiments.
Yeah, it's worth saying that the main driver for the Juno mission was the magnetic measurements. It was designed around being a magnetic probe, and the optical things were a bit of an afterthought.
Well, the optical things were, I mean, the main drivers was, in one respect, the magnetic probing, in another, gravity probing, simply by putting a spacecraft into that orbit with a high stability transmitter, and partly also the microwave radiometer for sensing the atmosphere down below the clouds. So, so those, I think, from our point of view, Juno's three most important experiments. And then there's also all the studies of the aurorae. taking advantage of the polar orbit. But as you say, JunoCam was a bit of an add-on intending for public outreach, but I think it was really no surprise, given the quality of the camera, that it's also produced a lot of good science. I mean, some of this being science observing phenomena at high resolution, which are being observed at lower resolution from Earth, and other good science of the polar regions themselves, which have never been observed before. Of course, that's something else I haven't been able to touch on in this talk.
Right, well, I think we've dealt with all the questions now, and we've been on for an hour and 5 minutes. So I'll thank John very much for such a fantastic talk, and encourage you all to start looking at Jupiter in the morning sky, and send us your drawings, images, and that's all for this month. I'll tell you about the next seminar, webinar will be on the 11th of August, and we will have Callum Potter talking about electronically assisted astronomy, which sounds like rather a big subject, so we'll have to see what that's about. But he gave us a talk about new methods of controlling telescopes to the equipment and techniques section at a meeting before lockdown, so it may be that kind of thing. And then in September the 15th, we have a talk from John Mason, Director of the Meteor section. Thank you all very much for joining us, and I will end the webinar now and then close down the YouTube feed. And of course, the webinar will continue to be visible on the BAA YouTube channel.
So many thanks to everyone who's been attending.
Thank you all. Bye-bye.
Bye.